Students, today let us discuss on multispectral versus hyperspectral remote sensing. Next slide please. See, in case of multispectral remote sensing, we normally gather the data in more than one wavelength of the electromagnetic spectrum. That means it is defined as the collection of reflected or emitted or backscattered energy from an object or area of interest in multiple bands. That means simultaneously recording the signals in more than one wavelength of the electromagnetic spectrum. Whereas in case of hyperspectral remote sensing, we normally gather the data in hundreds of spectral bands. See, instead of cameras and 1 to 4 bands for photogrammetry, normally in photogrammetry we make use of these aerial photographs. Of course, now we have our own Cartosat satellite, which is also used for cartographic applications. So, aerial photogrammetry as well as space photogrammetry, satellite photogrammetry we say. So, remote sensing use detectors that are sensitive to multiple bands to hundreds of bands in the electromagnetic spectrum, and normally detectors records the data and it is normally stored in BSQ, that is band sequential format, or band interleaved by pixel, or band interleaved by line. See, in case of multispectral, just now I said we are collecting the data in more than one wavelength of the spectrum. That means, for example, we have Landsat satellite which is carrying a sensor called multispectral scanner, which collects the data simultaneously in more than one wavelength of the electromagnetic spectrum. So we are simultaneously recording the data with more than one wavelength of the electromagnetic spectrum. Whereas in case of hyperspectral remote sensing, huge numbers of contiguous bands, that means there is no break between the bands, then hyperspectral remote sensing provides a continuous, essentially complete record of spectral response of materials over the wavelengths considered. Normally we start from 400 nanometer or 0.4 micrometer up to 2.5 micrometer, that is 2500 nanometer, 400 to 2500 nanometer with contiguous bands. There is no break between the bands in case of hyperspectral remote sensing. So now let us discuss in detail about the multispectral sensors. Multispectral, just now I said we are collecting the data in more than one wavelength of the electromagnetic spectrum. For example, Landsat MSS, which normally collects the data in 4 bands. You have the green band 0.5 to 0.6, then red band 0.6 to 0.7, then we have 2 near infrared bands 0.7 to 0.8 and 0.8 to 1.1. Whereas thematic mapper collects the data in 7 different spectral bands, of which 3 are in the visible region, 1 in the near infrared, 2 in the shortwave infrared, and 1 in the thermal region of the electromagnetic spectrum. So like that we have the latest in the Landsat enhanced thematic mapper, which collects the data in 8 different spectral bands. So we have spot fringe satellite carries a sensor called high resolution visible imaging sensor, which collects the data in 3 bands. Then we have HRV2 Indian remote sensing satellite linear imaging self-scanning sensor, which collects the data normally in 4 bands. LIS2 also collects the data in 4 bands. Then we have LIS3, 3 bands like that. These are some of the examples for multispectral sensors. Normally hyperspectral remote sensing involves the data collection in hundreds of bands. So we have some examples like Avery's and all. The detectors present in the hyperspectral sensors record the signals in hundreds of bands of the electromagnetic spectrum. So here we have, just now I said about the Landsat program. Landsat 1, 2, 3 carried multispectral scanner and return beam Vidicon sensors. These were the multispectral sensors collected the data. These are some of the specifications of Landsat MSS. It is a multispectral. Then we have thematic mapper. See, in Landsat 4 onwards, they introduced an advanced sensor called thematic mapper. Of course, Landsat 1, 2, 3 were having RBV, return Vidicon, and multispectral scanner. Whereas in Landsat 4 onwards, they removed RBV and they retained multispectral scanner. Then they added one more advanced sensor called thematic mapper, which used to collect the data in 7 different spectral bands. And from Landsat 6 onwards, they introduced an advanced sensor called one more sensor, enhanced thematic mapper plus, which collected the data with 8 different spectral bands. and which were almost identical to that of the thematic mapper, and these are some of the other specifications, repeativity and its path width and all. Next slide. See, in hyperspectral remote sensing, on a moving platform, we gather the reflected or emitted energy of the Earth's surface, and which records the data in hundreds of spectral bands. See, for example, Avery's data, airborne, visible and imaging spectroradiometer, using that they collected the data in 224 bands, and there the bandwidth is very, very narrow. See, for example, in case of multispectral scanner, the bandwidth is 500 to 600 nanometer, there is a difference of 100 nanometer. Whereas here, see, the bandwidth is just 5 to 10 nanometer, and simultaneously it records the signals. With this kind of imaging capability, it is possible to detect and identify unique trends in land and atmospheric data sets with better accuracy, because the purpose of using remotely sensed data is to gather more and more information. Multispectral information provides the required information, but it is better to go for hyperspectral, wherein we can differentiate more number of surface features. Even the species level identification is possible with hyperspectral remote sensing. And now let us see the major differences between multispectral and hyperspectral. Multispectral instruments can discriminate materials. Yes, for example, you have two different types of vegetation, coniferous and deciduous. Deciduous means broad-leaved species, coniferous means narrow-leaved species. If you want to differentiate, yes, we can differentiate that kind of surface features based on multispectral data. The concept is, see, different Earth surface features will behave differently when an electromagnetic radiation is incident upon that. Part of the light will be reflected, part is absorbed and part is transmitted. Added to that, they behave differently at different wavelength of the electromagnetic spectrum. Normally, satellites gathers the data in more than one wavelength of the spectrum. That means you have the blue band 0.4 to 0.5, 0.5 to 0.6, it is green, 0.6 to 0.7 micrometer, it is red, 0.7 to 1.1 micrometer, it is the near infrared. Like that, we are getting multispectral data. In case of, I am giving the example of Landsat MSS, which collects the data normally in 4 bands. Like that, multispectral data gathers the required information in more than one wavelength of the spectrum. So here, hyperspectral imaging is required to actually identify the materials. Here we can discriminate the materials using multispectral, and again the species level identification is possible with the help of hyperspectral, because the bands are very, very narrow and they are contiguous. So again, the multispectral data are used to detect the existence of various materials. So where we have the Earth surface features, what type of Earth surface features are there. But in case of hyperspectral data, which allows the identification of many materials, even in the mixed materials, normally whenever we go for identification of the Earth surface features, we are mainly interested to know the spatial resolution. Spatial resolution means if it is 30 meter object of the Earth surface can be differentiated by a sensor, but in that 30 meter, whatever the surface features are there, that average reflectance will be recorded by the sensor. In case of hyperspectral remote sensing, it is possible to differentiate whatever the features existing in that 30 by 30 meter area. So if you have mixed surface features, that can be differentiated. So here, greater accessibility due to the larger number of space-based multispectral sensors. See, in case of satellites, most of the satellites are carrying multispectral scanners. For example, we have Landsat program, we have Spot satellites, we have NOAA series of satellites, we have Indian remote sensing satellites like IRS-1A, 1B, 1C, 1D, we have P4 OceanSat satellite, we have P5 Cartosat, we have P6 ResourceSat satellites and all. So space-based, most of the space-based satellites are collecting the data in multispectral mode, because still we have to achieve this, because most current hyperspectral sensors are airborne. It is mainly the data is being recorded using the aircrafts. So we have the hyperspectral sensors mounted on aircrafts. They detect the reflected or emitted energy from the lower altitude, hence inaccessible in the Indian context. But now we have our own satellites called hyperspectral imager. With that, we will be able to gather the required information. So of course you can see multispectral versus hyperspectral. See Hyperion, then we have, these are the hyperspectral, EO Earth Observer, then Landsat 7 ETM. But here see, you can get the, we can see, these are the main differences between a multispectral, these are the multispectral, whereas this is the Hyperion, hyperspectral sensor. See, dip and valley, even at a narrower wavelength we can get the required information, and with this we can identify more number of surface features. Next slide. See, in hyperspectral remote sensing, which records energy over several separate wavelength ranges, so at various spectral resolutions, these are referred to as multispectral. Normally in hyperspectral remote sensing, the weightage will be given more to the spectral resolution, because we have more number of spectral bands. I said in the beginning, we have number of spectral bands and which will be contiguous. There is no break between the bands. That means if it starts at 400, it ends at 2500, and we can gather the required information with very, very narrow bands. And here the advanced multispectral sensors called hyperspectral sensors, which detect hundreds of very narrow spectral bands throughout the visible and near infrared. Throughout the visible means, just now again I am repeating, 400 nanometer to 2500 nanometer. You can gather the required information without any break. With 5 nanometer interval or 10 nanometer interval, you can gather the required information in hundreds of spectral bands. And even the mid-infrared portion of the spectrum is also used. That means 400 to 2500 covers the visible, near infrared and short wave or mid-infrared region of the spectrum. And see, here itself it says narrow bands, less than 20 nanometer normally in resolution, and it will be contiguous measurements. And it is also called as imaging spectroscopy or imaging spectrometry, the simultaneous acquisition of images in many relatively narrow, so that is very important in hyperspectral remote sensing, very, very narrow bands, and which should be contiguous. This is one of the major thing in case of hyperspectral remote sensing. It is contiguous bands, spectral bands. Then throughout the ultraviolet, visible and infrared portion of the spectrum also we can gather. The very high spectral resolution facilitates fine discrimination between different targets based on their spectral response in each of the narrow bands. So here the bands are very, very narrow, and the weightage is given to the spectral resolution. Then we have hyperspectral remote sensing, again allows a sensor on a moving platform. So here we are recording the reflected or emitted energy with 5 to 10 nanometer bandwidth and all. Even we can go up to 20 nanometer bandwidth, but which should be contiguous. There should be no break between the bands. Whereas in case of multispectral, there will be a break between the bands. For example, in case of thematic mapper data, if the first band collects the data from 0.45 to 0.52, part of blue and green, second band collects the data from 0.52 to 0.59, the second, that is green band, the third band collects the data from 0.62 to 0.68. That means there is a break between 0.59 to 0.62 micrometer or 590 nanometer to 620 nanometer. But whereas in case of hyperspectral remote sensing, there is no break between the bands. So with such detail, the ability to detect and identify unique trends in land and atmospheric data sets is greatly improved. See, by the development of this hyperspectral remote sensing, now we will be able to differentiate more number of surface features. This all technological advancement taking place in the field of remote sensing. See, we have hyperspectral platforms, first hyperspectral scanners. So this was experimented during 1982, airborne imaging spectrometer. Then during 1987, again Avery's airborne. See, this the platform used here is airborne, not the space platform, but they used the visible and infrared region of the electromagnetic spectrum for imaging the surface features. Then again during 1995, hyperspectral digital imagery collection experiment, HIDIS, then Hyperion Earth observation. See, most of these experiments were carried out by USA, NASA of USA and other space agencies of USA. Next slide. See, hyperspectral cube, when we talk about the hyperspectral cube, which shows the volume of data returned by imaging instruments. Imaging instruments means we have the airborne platforms, we have the spaceborne platforms. With that, we will be able to gather the required information illustrates how data from imaging instruments is georeferenced. See, there is a need for georeferencing and all at the end after getting the satellite data we have to do, because it should match the Earth surface features. For that purpose, normally we are making also these topographical maps or ground control points, and data from different wavelengths can be used to create a map. See, normally in remote sensing, the end product will be a map. So it should be a cadastral map or thematic maps. Normally we go for different kinds of thematic maps in either true color or false color infrared formats. See, normally one can generate the true color imagery where the vegetation is represented by green color, but in the case of false color composite, the vegetation is normally represented by red color. The fact is, vegetation reflects maximum light in the near infrared region of the spectrum. So we have few more examples for airborne sensors, and I said in the beginning, most of these airborne sensors, hyperspectral remote sensing is being practiced with airborne, that is aircrafts are used, airborne visible, and that is NASA of USA, they launched this, carried out this experiment with the 224 band, see, 0.4 to 2.5 micrometer or 400 to 2500 nanometer region, and the sampling interval and resolution, see, less than 10 nanometer. That means if you go through 2100, the difference is you have around 224 bands. See, field of view again is provided here, 30, then 614 pixel swath. The swath width means how much area it covers at a particular instant of time. Then we have high spectral mapper. Australia launched a hyperspectral sensor. Then 126 channel sensor covering. Again, see, the bandwidth is from the visible up to the mid-infrared. We have visible, near-infrared and mid-infrared portion of the spectrum is being covered here. Then digital airborne imaging spectrometer, it carried 72 channels. See, again, the bandwidth is almost same. In most of the cases, they go from visible to the mid-infrared region of the spectrum. So 8 to 12 nanometer bandwidth. Then CASI compact airborne spectrographic image. Canada launched this with 288 spectral channels, and the bandwidth was about 1.9 nanometer. And see, these are some of the specifications of hyperspectral. Especially the experiment is being carried out using airborne, because we do not have number of satellites carrying the hyperspectral sensor. From the lower altitude, using aircraft, they made this experiment. Next slide. See, airborne continuation of that. Just now I said 224 bands ranging from 400 to 2500 with 10 nanometer. So Australia also launched the satellite. Then few more countries, European Space Agency, Canada and all, launched few more hyperspectral sensors. And this is the experiment. Airborne, see, airborne is the platform. Visible and infrared, that is the electromagnetic spectrum. Imaging, spectroradiometer, airborne, visible and infrared imaging, spectrophotometer or spectroradiometer. This is how, using aircraft, they carried out the experiment. Next slide. See here, what are the specifications of AVIRIS? It carried 224 individual charge-coupled devices that are the detectors normally used. Charge-coupled devices are electronic silicon chips which are more sensitive to light than the ordinary films. So here you can gather the required information using charge-coupled devices. See the spectral resolution. So again, in the case of hyperspectral remote sensing, the weightage is given more to the spectral resolution rather than the other kinds of resolutions. We have spectral, spatial, temporal and radiometric resolution. Here the weightage is given to the spectral, the bandwidth. Bandwidth means the difference between two. When I say 10 to 20, the difference is 10. That is the bandwidth, 10 nanometer. Spectral resolution of 10 nanometers. Then spatial resolution of 20 meters at typical flight altitude. The spatial resolution was also here a little bit high, 20 meters. Then flight platform, that is NASA's experiment using their aircraft. Then flight altitude and all. These are some of the specifications of this AVIRIS. So the total interval reaches from 380 to 2500 nanometer, roughly the same as TM band range. So 380 means that is part of visible. See, visible starts from 400. This is the adjoining part, that is UV part of 380 UV. 2500 short wave or mid-infrared portion of the spectrum, and which images the Earth surface with push broom succession of lines each containing 664 pixels. That means we have the push broom, we have whisk broom scanners and push broom scanners, along track scanners and across track scanners. Whisk broom scanners are also called as across track scanners. Along track scanners are also called as push broom scanners. There is no moving part. A linear array of detectors are there. They simultaneously record the signals. That is the push broom. See, this is the average concept. See, you can see the peak and dips. See, absorption bands as well as the reflection. So mainly, if you have minute differences on the Earth surface, that can be differentiated with this absorption bands and all. Each spatial element has a continuous spectrum that is used to analyze the surface and atmosphere. See, with 224 spectral bands, they have been collected simultaneously. All these 224 bands of data has been collected simultaneously, and you are making use of the visible to short wave infrared region of the electromagnetic spectrum. That means minute differences of the Earth surface features can be differentiated with the help of hyperspectral remote sensing. So here, hyperspectral remote sensing is a combination of imaging and spectroscopy in a single system, which often includes large data sets and require new processing methods. Of course, you require a different software package for these purposes, because we have to handle enormous data, maybe 200, 300, 400 channels of data, and which involves the acquisition of image data in many contiguous spectral bands, so which is being recorded at different wavelengths of the spectrum, but there will be a continuous, there is no break between the bands, and ultimately producing laboratory quality reflectance spectra for each pixel in an image. Each pixel, in the sense, pixel is nothing but a picture element. When we talk about a satellite data, which is made up of rows and columns, so you have the scan lines, and in each scan line you have number of pixels. Pixels represents the spatial resolution, the dimension represents the spatial resolution, and it is recorded by a DN number, which is also having a digital number, which is its radiometric sensitivity, and at what wavelength of the spectrum the data is being recorded. That is called as its spectral resolution. So we have hyperspectral data sets are generally composed of about 100 to 200 spectral bands of relatively narrow bandwidths. Again, I am repeating, see here the bandwidths are very narrow, whereas in case of multispectral the bandwidth may be 100 nanometer or 200 nanometer, whereas here it is just 5 to 10 nanometer. Then the ample spectral information provided by hyperspectral data is able to identify and distinguish spectrally similar materials. See, the purpose of going for multispectral data is to differentiate the Earth surface features. When I am not in a position to differentiate two surface features at one particular wavelength, I will go for another band, multispectral. We have 4 bands, 7 bands like that. But in hyperspectral, we have hundreds of spectral bands, and with the narrow bands, I will get more and more information, but at the same time, I have to handle enormous data. So here, it is typically represented as a data cube with the spatial information in the x and y dimension, that is x and y plane, and spectral information in the z direction. So you can see here the spatial, the minimum area of the ground which can be resolved by a sensor, and this is the number of bands. Yes, you have hundreds of spectral bands. See, red, green and blue. By combining this, you can generate a color composite, and here you can see the spectral reflectance curve. See, reflectance versus wavelength. If you plot the spectral reflectance versus wavelength, we are getting the spectral reflectance curves. See, the purpose of plotting the spectral reflectance curve is to get the required information, which are the best bands for a particular application, where I have the peak reflectance, where I have the dips. Again, there you have the peak and dips. So where you have the higher reflectance, where you have the absorption bands and all. Based on that, you will be able to differentiate the surface features. Next slide. See, here again, the requirement of spectral resolution is determined by the width of the occurring absorptions. See, reflection or absorption, here it is at what wavelength of the spectrum the surface features absorbs the electromagnetic radiation. For soils and geological investigation, see, mostly in the near and short wave infrared at 10 nanometer resolution is necessary. 10 nanometer will be the bandwidth, so that from 400 to 2500 you will have around 200 watt spectral bands. With that you can differentiate the soil and geological features with a better accuracy. See, for example, if you have the band 445 nanometer to 620 nanometer, with this much of bandwidth you can differentiate for what applications we can make use of. See, for vegetation differentiation, water, and if there are ferrous-rich minerals, yes, that can be differentiated. Then 683 nanometer to 720 nanometer, and the bandwidth is again 5 to 10. You can differentiate the vegetation, and 745 nanometer to 765. Then band interval is 5 to 10 nanometer. So vegetation, atmospheric correction, and all we can carry out, because there is a influence of the atmosphere. Before the energy reaches the earth's surface, it has to pass through the atmosphere. When the energy passes through the atmosphere, we have the scattering effect and all that has to be minimized or removed before making use of any satellite data for a particular application. So then 780 nanometer, so 5 to 10 nanometer interval. See, we can go for vegetation and ferrous-rich mineral differentiation. Of course, this is again the near infrared band 880 to 1035 with 5 to 10 nanometer. Again, we can differentiate vegetation and ferrous-rich minerals. So it is continuing. So in the short wave infrared, see, after visible we have near infrared, then we have the short wave near infrared, short wave infrared. We can determination. See, suppose we want to determine the soil moisture. Yes, optimum spectral resolution is this much. The band interval should be 50 nanometer. Then weak absorption bands of carbonate, dolomite, and calcite. See, that takes place at this particular wavelength with this interval. So then characteristic absorption bands of carbonate, OH, and sulfate bearing minerals. See, this is actually the band at wavelength, and this is the bandwidth. Broad carbon, see, CO3 bands in carbonate, calcite, dolomite, OH and AiOH bearing minerals like iolinite, muscovite, allanite, etc. Again, these minerals can be differentiated with the help of very, very narrow bands. See, there was one experiment being carried out called Omega. Again, it is a hyperspectral sensor, Omega, and here it used the visible and infrared mineralogical mapping spectrometer. Of course, hyperspectral remote sensing is one of the best tool for geological applications. With that, we can differentiate more number of surface features, especially related to rock types and minerals. 352 contiguous spectral bands covering 0.35 to 5.1 micrometer, and spectral resolution of 7 nanometer to 20 nanometer, and spatial resolution, of course, it is little bit coarser, 0.3 to 4 kilometer per pixel. Then, see, in case of India too launched few hyperspectral sensors, and this was experimented when India launched the satellite to moon called Chandrayaan-1, and Indian mini satellite on hyperspectral imager launched in April 2008. See, we launched few satellites with the spaceborne, so it is not airborne, spaceborne, and number of bands, see, 64 and 512 bands. Spectral separation was 8. Spectral range was 0.4 to 0.95 microns. Spatial resolution was, of course, little bit coarser, 550. Quantization level, this is nothing but the radiometric resolution. 8 means 2 to the power 8 means it is 256, 9 is 512, 10 is 1024, and this is 2048 quantization. 11 bits, that means 0 is the darkest. 0, it is represented by a DN value of 0. If it is represented by a value of 2047, that will be the brightest signature in this. So repeativity was about 24 days. Next slide. So in Chandrayaan-1, see, there was again hyperspectral imager. 64 contiguous bands in the visible and near infrared. Spectral range was 0.4 to 0.95 micrometer. Spectral resolution of better than 15 nanometer. Spatial resolution of course 80 meter. Swath coverage of 20 kilometers. Swath width means how much area it covers at a particular instant of time. So that much area's radiation will be recorded by a sensor of a satellite. Then Chandrayaan-1 moon mineralogy mapper called MMM. 86 contiguous bands in the visible and near infrared. Spectral range 0.4 to 3 micrometer region. See, visible up to beyond little bit short wave infrared. spectral resolution of better than 10 to 40 nanometer, spatial resolution 70 to 140 meter, and swath coverage of 40 kilometer. These are some of the specifications and how best we can make use of this hyperspectral imaging satellite. So what are the sensors available, and we have discussed, and its specification is an Earth observation satellite which is providing hyperspectral imaging services to India for a range of applications. See, in the field of agriculture, see what type of crops are grown in an area and how much area is coming under paddy, sugar cane, wheat, maize, jowar and all. I can calculate the areal extent, and based on the healthiness of the vegetation, even we can calculate the yield. But in a small area, maybe a farmer may be having 2 hectares of land. In that 2 hectares of land, he might have gone for number of different types of agricultural crops. So each can be differentiated with the help of hyperspectral remote sensing. Multispectral can differentiate where you have the agricultural area, where you have the forest area. But in the case of hyperspectral remote sensing, again when you are concentrating on agriculture, see what type of crops are grown, how much area is coming under sugar cane, how much area is coming under paddy and all, and even forestry where you have the deciduous forest, mixed vegetation, bamboo vegetation, coffee plantations are there, tea plantations, rubber plantations. See, that kind of species level differentiation is possible. And in the assessment of geography such as coastal zones and inland waterways, again we can make use of this for coastal related studies and hinterland water bodies. The data will also be accessible to India's defense forces, especially for defense purposes they are making use of. Before hyperspectral imager, other Indian hyperspectral imaging payloads were high-C hyperspectral imager on IMS-1 and Chandrayaan-1, and LIV high-C limb viewing hyperspectral imager on YouthSat. These are some of the specifications of Indian hyperspectral imaging systems. Next slide. See, hyperspectral sensors on Mars orbit. This is test thermal emission spectrometer. In fact, this type of satellites are very useful to know more about the Mars. On board the Mars Global Surveyor 1997, of course NASA launched this satellite, will be covered in the thermal remote sensing. See, it is normally collects the data in the thermal region of the spectrum also. Omega visible and infrared mineralogical mapping spectrometer, and on board the Mars Express 2003, European Space Agency, then compact reconnaissance imaging spectrometer for Mars on board the Mars Reconnaissance Orbiter, again launched by NASA of USA. These are some of the. Now let us see some of the basics of geological spectroscopy. And see, I said imaging spectroscopy. It is also called as imaging spectroscopy, hyperspectral remote sensing. We are calling it as spectroscopy. And how best it can be used for geological applications. See, spectroscopy is the study of interaction of electromagnetic radiation. Yes, we have the electromagnetic radiation ranging from gamma rays up to radio waves, of which visible, infrared and thermal region of the spectrum are very useful for terrestrial remote sensing. And see, terrain elements and the result of such interactions are presented as absorption features in the reflected spectra of terrain elements. Photons enter a mineral, some are reflected from grain surface, some pass through the grain, that is called as transmittance, and some are absorbed. So there is reflection, absorption and transmittance. This will vary for different Earth surface features. See, photons or electromagnetic radiations are selectively absorbed in minerals by atomic process operative within constant minerals. The variety of atomic processes involved and their wavelength dependence is the key to derive information about the chemistry of a mineral from its reflected light. Yes, here we are deriving the composition, the chemistry of a particular mineral based on its reflectance, how it behaves. The most common electronic process responsible for imprinting absorption features in the reflected spectra of minerals is related to movement of electron from one energy level to next higher energy, higher order unfilled electron level or shell, that is for example iron. Absorption bands can also be caused by charge transfer or inter-element transition, where the absorption of a photon causes an electron to move between ions or between ions on ligands. See, these are some of the specifications, especially hyperspectral remote sensing can be used in a better way to delineate different rock types, different minerals and all. So spectral features imprinted in the reflectance spectra in visible and near infrared wavelength range are indicative of the presence of or absence of transition metal ions. Example, ferrous, chromium, cobalt, nickel, resulting in absorption features due to electronic processes. The presence or absence of water and hydroxyl, carbonate, sulfate, etc. determine absorption features in the shortwave infrared region due to vibrational processes. Some of the specifications, especially hyperspectral remote sensing, is very much gaining importance. And if you have sufficient knowledge of hyperspectral remote sensing, this can be effectively used to get more information regarding geology. In general, absorption band depth is correlated with the relative amount of material present, especially for monomineralic minerals. See, for example, some of the rocks are made up of a single mineral. So, for example, olivine, which is made up of not olivine, some of the minerals are made up of single minerals. In addition, absorption band depth is also related to grain size. In thermal infrared domain, spectral, that is emissivity, are result of vibrational molecular motion. 8 to 12 micrometer is known for intense feature of silicate. Spectral feature in the thermal infrared region shifts towards shorter wavelength as bond strength within the lattice increases. See, normally here we are using 0.4 to 2.5 micrometer or 400 to 2500 nanometer range of the electromagnetic spectrum. Slide. See, these are some of the references. See, if you want to get more information regarding hyperspectral remote sensing, of course, this is one of the best technique for identifying different Earth surface features. And I said in the beginning, using multispectral scanner, you can identify a particular surface feature. And if you want to differentiate individual surface features present in an area, it is better to go for hyperspectral remote sensing, where the data is being recorded in hundreds of spectral bands and they are contiguous bands and there is no break between the bands. And if you want to have more references, yes, you can visit Wikipedia or Indian Institute of Remote Sensing, Dehradun. In fact, they have done a lot of work, and you can visit Indian Space Research Organization websites, and they too have launched a number of satellites. And even if you visit, see, Anidam Guha, Geosciences Group, NRSC, ISRO, Balanagar, Hyderabad. Again, at Balanagar, they are doing a lot of work. That center is called as National Remote Sensing Service Center. And so far, I have discussed in detail about the advantages of multispectral and hyperspectral remote sensing. Thank you.